Sounds good. Okay, thank you for coming. Welcome to the past, present, and future of Apache Storm. My name is Taylor Goetz. I'm part of the engineering staff at Hortonworks. I'm also the PMC chair of Apache Storm. I'm an ASF member, and I'm also involved in a number of other projects, including the incubator. So before we get into the new stuff, we'll go through a little bit of history. So Apache Storm 099X, that release line was when Storm first came to Apache. That was our first initial official Apache release when Storm became a top-level project. We also went from 0MQ for our internal transport to NETI, and that decision was in large part because 0MQ is LGPL and the license is not compatible with Apache. We also expanded integration. Before we moved to Apache Storm, the distribution was pretty much standalone, and any connectors to external systems like Kafka, HDFS, and HBase were all separate GitHub projects, and they were forked multiple times, and it was really difficult for people to figure out which version worked with what. So we brought in those connectors into the official release so that when we released, everything was supported and in one centralized location. And during that time, we also started to address dependency conflicts. So that's where user code or users' dependencies and Storm's dependencies conflicted. I don't know if anyone's ever fought with Guava dependencies. You know what I'm talking about. The 0.10x line was all about enterprise readiness. And what that mainly meant was security. So that's when we introduced Kerberos authentication across the board so that all components in a Storm cluster are authenticated. And it also supported some user isolation capabilities, the ability to run topologies as a specific user, and also multi-tenancy. That's also when we introduced the ability to do rolling upgrades. So being able to upgrade your cluster from 0.10.0 to 0.10.2 without having to shut down or undeploy any of your topologies. We also introduced Flux. Flux is a declarative topology wiring tool / framework where you can define and wire together your topologies using a YAML file that's external to your actual topology jar file. So rather than changing configuration and having to repackage your topology, you just change that external configuration, redeploy, without having to repackage everything. We also started expanding some of the groupings. So stream groupings like fields groupings. With field groupings, you can get skew, and partial key groupings address that by doing partial groupings based on a key. We also moved to Log4j to improve logging performance, or Log4j 2. We added Hive integration, Microsoft Azure Event Hubs integration, Redis support, and also JDBC integration as well. So Apache Storm 1.0 was released just about a year ago, and that release was all about maturity and performance improvements. One of the first things we introduced with that was Pacemaker. What Pacemaker is a heartbeat server. So prior to Pacemaker, and Pacemaker it's an alternative to Zookeeper. You can still use Zookeeper, but for very large deployments like they do at Yahoo, where they have thousands of nodes, they use Pacemaker. So it's an alternative to Zookeeper. It's essentially an key value store that stores its values in memory, and that allowed it to scale from 2,000 to 3,000 nodes per cluster. And Pacemaker also integrates with the rest of Storm security. For example, Kerberos and digest authentication. The distributed cache API in 1.0 introduced external storage for topology resources. So prior to this, what a lot of people did with things like lookup dictionaries, machine learning models, geolocation data, essentially any data that your topology relies on, people would package that in their Storm jar and deploy it. And then in order to change any of those things, you'd have to repackage and redeploy. So what the distributed cache, and sometimes you'll hear it referred to as a blob store, allows you to do that outside of your topology. So you can upload your resources to the blob store, and then your topology can periodically refresh that from the blob store. There are two implementations. One is based or backed by HDFS. So HDFS handles all the replication. There's also a local file system one where Storm itself handles the replication. So the contents of the blob store are replicated across the entire cluster. And it also allows you to share that data between topologies. You can also update that content from the command line. It also supports automatic compression, so if you upload a zip, when that gets replicated to the supervisors where your workers are running, it will automatically unarchive it so your topologies can use it. HA Nimbus, prior to this, Nimbus was what I call a soft point of failure, meaning if Nimbus went down, your deployed topologies would still operate and run, but you wouldn't be able to submit any additional topologies. With HA Nimbus, you can specify any number of Nimbus nodes, and if one goes down through Zookeeper, they'll perform leader election and a new Nimbus will come up. So it overall increased the availability of Nimbus. It also leveraged the distributed cache API for replicating topology contents. And the replication guarantees that those files are available to every Nimbus and supervisor in the cluster. In 1.0, we also introduced state management, so essentially stateful bolts. So with stateful bolts, you, rather than extending the basic bolt, there's another base class called stateful bolt, and when you do that, in the background, Storm will automatically checkpoint and save the state. So essentially you have like a key value store inherent within your topology that you can query and update, and Storm will automatically checkpoint that state. It was based on the asynchronous barrier snapshotting algorithm and also the Chandy Lamport algorithm. But you'll see these, that's a common theme, as I believe Apache Flink uses the same mechanism, similar mechanism. We also introduced streaming windows. So both sliding and tumbling windows. Sliding window is a window that slides where windows can overlap, and tumbling are similar, but windows do not overlap, they're distinct. With streaming windows, you can specify the length as either a duration, temporal duration, or a tuple count. Then a slide interval, which is how often you advance the window. It supports a number of different timestamps, event time being the time the event actually occurred before it came into the system, ingestion time, the time that it actually hit the system, and then processing time, which is the time when Storm actually performed the processing on that data. It also has support for out-of-order tuples and late tuples and watermarks. And like the stateful bolts, windowing leverages the same mechanism to checkpoint the state. So if a worker goes down, when it comes back up, it can restore the window state. Storm 1.0 also introduced back pressure. So prior to this, the only way to throttle things was turn on acking so that reliability is guaranteed, so that every tuple gets acked, and then throttle the spout by setting max spout pending, which is how many tuples can be in flight before the spout starts to throttle itself. With automatic back pressure, you can specify a high and low watermark, which is expressed as a percentage of the internal buffer size. And then there's a thread that monitors those buffers. And if the high watermark is reached, it throttles the spouts. If the low watermark is reached, then it stops throttling. And this is completely independent of spout implementation. So all spouts that Storm support also support automatic back pressure. We also introduced the resource-aware scheduler. What the resource-aware scheduler does is allow you to specify resource requirements in terms of memory and CPU for individual topology components like spouts and bolts. In terms of memory, it allows you to specify both on-heap and off-heap if you're using off-heap. Not many people use off-heap, but some people do, and we support that. For CPU, it's because of different CPU architectures, we had to use a point system. So essentially you define your sort of own arbitrary values for the different types of processors or cores on your machines. When using the resource-aware scheduler, it's important to know that the resource requirements are per component instance. So parallelism of your components is important because it affects how that calculation is made. So for example, if you say I want 50 CPU points for this spout, and you set the spout parallelism to 2, then that's going to take up 100 points. So some of the usability improvements in 1.0 were enhanced debugging and monitoring of topologies. Dynamic log levels. Prior to this, if you've ever wanted to change the log level settings for a topology or for a supervisor in the cluster, you'd have to SSH into each machine in the cluster, change the log4j configuration, then wait for it to take effect, do your debugging, then come back and undo it all. What this allows you to do is via either the command line or the Storm UI, you can set a log level. So it's essentially a log4j configuration, and you can set it to debug, whatever, and also set a optional timeout. So after that timeout, the changes will automatically be reverted. So again, you can do this from the UI or the command line, and you never have to SSH and do all that. Then you can also search those logs from the Storm UI and the Storm UI log viewer. On-demand tuple sampling. How many people here have written bolts or trident functions just for the purpose of debugging output? Well, with this, you don't have to do that anymore. And almost every Storm project I've seen when I work with customers, I see this debug bolt, and I'm just like, so with this, you don't have to do it anymore. What you do is, in Storm UI, you select a topology, either the topology as a whole, or an individual component, such as a spout or a bolt. and then click the debug button. You specify a sampling percentage, which is the percentage of tuples that are going to be sampled. Then when you click on the events link, it'll give you a log of all those events, of all the tuples that traveled through during the sampling period. Distributed log search allows you to search across all log files in the cluster for a specific topology. Prior to this, again, to access the log probably meant SSHing into one of the workers and tailing a log. So what this allows you to do is directly from the UI, search across all of them. When you issue your query, that query will be sent to each supervisor in the cluster. Then all the results will be aggregated and sent back to you. It also allows you to search in archived or zipped logs. And as I said earlier, all the results include matches from all the supervisor nodes. Another feature added to the Storm UI in 1.0 was dynamic worker profiling. And what this allows you to do is request worker profile information from the Storm UI, such as heap dumps, JStack output, and JProfile recordings, and then download the generated files for offline analysis using whatever heap analysis or JStack analysis tool you want. And it also allowed you to restart workers from the UI. Supervisor health checks were a way to identify supervisor nodes that were in some form of a bad state and decommission them. And the way this is implemented is you define what unhealthy means via shell script. And Storm will periodically run that shell script, and if it returns a specific code, that indicates that the supervisor node is unhealthy, and Storm will decommission that node if that occurs. For 1.0, one of the biggest features was improved performance. We got up to 16 times faster throughput and greater than 60% latency reduction. And a lot of that came down to some internal changes in the way we handle buffers between workers and tasks, and doing some internal batching at the transport level. Even though all events are processed one at a time, there's some batching and buffering between those queues. With Storm 1.0, we introduced support for Cassandra, so bolts to write to Cassandra, Solar, Elasticsearch, and MQTT as well. So Storm 1.10 just came out this past week. One of the most interesting features of that is streaming SQL. So streaming SQL is powered by Apache Calcite. Apache Calcite is, I think, in my opinion, quickly becoming the de facto library for implementing CQL on big data systems. I know Flink's using it, and a number of other projects. I believe Hive is using it now, and we used it for Storm SQL. Streaming SQL was actually first available in 1.0, but we didn't advertise it because it was fairly experimental at that time. One of the main things it didn't support was parallelism of different components. But in 1.1, it's progressed enough that we've released it and announced it. So basically, to use that, what you do is you define your topology as SQL in a text file, and then use the Storm SQL command to deploy the topology. What Storm will do under the hood is generate a Trident topology and deploy that topology to the cluster and run it. Some of the features or external systems that it supports include Apache Kafka. So reading from Kafka via the Kafka Spout implementation, writing to HDFS, reading and writing to HDFS, MongoDB and Redis. Those are preliminary implementations that we have, but the actual connector interface is well defined. So to add additional systems, all you have to do is implement the ISQL Trident data source. So in the future, we'll probably be adding additional systems like HBase, Hive, Cassandra, and other systems.
Quick question. Isn't Trident a micro-batching system?
Yes, it is. And Trident was the first implementation. There may be another iteration where we move away from Trident. But we mainly went with Trident because Trident had some of the features like joins and that sort of thing that we needed support from without having to re-implement it using the Storm's core components. Some of the features it supports include tuple filtering, projections, as I mentioned earlier, user-defined parallelism of the generated components. We support comma-separated value, tab-separated value, and Avro input and output formats. And those input and output formats are also extensible in the same way that the data sources are. It's a simple interface to implement, and once you do that, you can plug in your input and output format. And I'll show you some examples of how that works. It also supports user-defined functions, and I'll show you some examples of that as well. So it allows you to define your own function, SQL function, specify a class for it. So this is what it looks like, or this is the basic syntax for connecting to an external data source. Say you create external table, give it a name, and then the optional input format and output format. If you don't specify that, it'll use text. And then location is actually, that's a custom field where you specify what that system is. And I'll show you examples of that. For example, a Kafka URL. Parallelism, I mentioned earlier. Table properties that allows you to customize things. So for example, in SQL, how do you tell something all the Kafka configuration information you need to connect to Kafka? It would look messy if you tried to do it in SQL, so that's usually a chunk of JSON that defines those properties in line. So here's an example of a spout connecting to Kafka, specifying a primary key and the fields that it expects to find in the messages coming out of Kafka. And for a spout, the location just needs to point to the broker URL. This is what it looks like to connect to Kafka as a producer, meaning we're writing to Kafka. And in this case, we need more information to tell the Kafka producer how to connect to Kafka. So in this case, where the Bootstrap server is, whether we're using Axe, then the class for the key serializer and the value serializer. So let's run through an example. In this case, we're going to consume Apache server logs from Kafka, filter out everything but errors, and then write the errors back to a separate Kafka topic. So this is our Kafka spout, specifying the fields that are coming in that log format, and then the location, which is the Kafka URL. Then for output, we're writing most of the same information, and those table properties should look familiar now, and our key serializer and value serializer. Then this is the insert and select query that we're actually using to move from the Kafka input to the Kafka output. So we're inserting into the Kafka Apache error logs topic and selecting from the Apache logs, and our where clause is where we say, okay, anything other than a 400, so anything in the 500 HTTP error code range will be selected. So next we'll look at what user-defined functions look like. There's no real, and this mainly comes from Calcite, there's no real interface that you implement. It's mainly method conventions, so method signatures. So this is a scalar user-defined function. So to create it, the SQL, we just say create function. And this one we're calling it add, and specifying the fully qualified class name for the class we created. And then in that class, for scalar functions, the convention is to have a method called evaluate. And here we just, for add, we just return the two numbers that came in. For aggregate user-defined functions, a little more complicated. The create function declaration is the same. And in this case, for aggregate functions, you have an init method, which returns the initial value, then add, which has the accumulator, which initially will be just the return value from init. So in this case, we just concatenate the two together, and then the result returns the string that came through the add method. Another thing in 1.1 is we added support for Kafka version 0.10 and later. So right now in the Storm distribution, you'll notice two Kafka connector. One's called Storm Kafka, and that's the older legacy version that's compatible with 0.8 and 0.9. And then we added Storm Kafka Client for Kafka 0.10 and later. And some of the improvements that includes are an enhanced configuration API. The older version, a lot of people had difficulty figuring out all the different configuration values, and it was confusing. So we broke out that API and revamped it so it's easier. It gives you a lot more control over offsets. So when you deploy a Kafka-based topology, where do you want it to start? So initially, do you want to start at the beginning of the queue, the end of the queue, where it last left off, a specific point in time, or a specific offset? So now you have full control over that. It also adds consumer group support. Pluggable record translators. So what that is usually when you get messages out of Kafka, you've got a key and a value, and the value is just a byte array. What record translators do is allow you to define a schema for that that translates that byte array into whatever values you want to emit into your topology. We also support wildcard topics and support for multiple streams. And as with the legacy Kafka integration, it integrates fully with Kafka security, including SSL and Kerberos. We added PMML support, which is predictive model markup language. And what that is an XML format for evaluating machine learning models. And usually the model is produced by data mining or machine learning algorithms. And then based on that, you get a model. and you can input data into that model and it will output scores and predictions. So what the PMML bolt does is it executes your model and then emits scores and predicted fields as tuples. And it gives you full control over how you want those values to be formatted and emitted. Currently, you can store the model in the distributed cache blob store to decouple it from the topology, or you can also include the model itself when you deploy the topology. One drawback we have right now is that if you store it in the distributed cache, you actually have to redeploy your topology to when that model changes. But probably in the next release, 1.1.1, we'll change that so that the bolt will periodically look at the model in the blob store, and if it's changed, reload it automatically. So in that case, you could, if your model changes, you just push it into the blob store, and the topology will pick it up and automatically deploy the new model. Druid, we added Druid integration. Druid is a high-performance column-oriented data store that's popular for real-time analytics and OLAP. And what we added was a Storm Bolt and Trident state implementation that write to Druid. And like most Storm connectors, there's a mapping mechanism. So there's an interface that you implement. Storm comes with default implementations, but if you want to customize that behavior, there's a interface that you implement that determines how a tuple, Storm tuple, gets mapped into Druid's storage structure. We also added OpenTSDB integration, which is a time series database based on Apache HBase. Includes both a Bolt and Trident state implementation. And then there's a default class that you can extend, or I'm sorry, not a default, an interface that you can implement to determine how that maps to OpenTSDB's data structure. And that structure consists of a metric name, tags, which are essentially metadata, name value collection, the timestamp, and then the actual value of the metric, the time series metric that you're storing. We also added a Kinesis spout for consuming from AWS Kinesis. Like other integration components, user-defined handlers, just a simple interface to implement. We include a default one. And it also includes user-defined failure handling. So when Kinesis burps, depending on what happened, you get notified and your specific logic kicks in. I believe, if I remember correctly, the default is just to requeue the failed messages. We added an HDFS spout, which lets you point to a directory in HDFS, and when a file lands there, the spout will lock onto it and start streaming the data into your topology. That locking mechanism is also what powers parallelism. So to parallelize it, let's say you want 5 instances reading from a specific HDFS directory. Each instance will lock onto a file and then prevent other ones from locking onto it. So you can have multiple instances of the spout reading from the same directory. Once those files have been processed, they get moved to a configurable archive directory. And then for corrupt files, so let's say a file lands and for some reason the spout can't process it because the data is corrupt or malformed in some way, it'll move that file into your configured bad files directory. And the HDFS spout also supports HDFS instances that are secured with Kerberos. I mentioned earlier what Flux is. It's that declarative tool for wiring together your topologies without externally to your package topology. In 1.1, we added visualization. So in Storm UI, you can paste your YAML into a field, and it will display a visual representation of the topology. It also now supports stateful bolts and windowing, named streams, and support for lists of references. So references allow you to define one component or a number of components and then reference them elsewhere in your YAML file. Topology deployment enhancements. This is an alternative to so typically with Storm you create an Uber jar, a shaded jar with all your topology dependencies in it. What this does is allow you to allow for topologies that are not packaged as an Uber jar. What you can do is specify any additional dependencies on the command line. So for -- jars, that will upload local files. And you can also specify dependencies as Maven artifacts if you use the artifacts flag. And what we'll then do is we'll resolve those dependencies, download them from whatever Maven repository they reside in, and then upload them to the Storm cluster. And the artifact repository flag also allows you to specify other repositories aside from Maven Central. I covered the resource-aware scheduler earlier. Some of the enhancements we made there include topology priorities. So you can specify, let's say you have a dev, prod, and test. And you want, obviously, prod to have the highest priority. You set a number for topologies with that flag, and those will automatically get the most resources. It also allows you to specify resources per user. So let's say user Taylor has 1,000 CPU points and 20 gigs of memory, and some other user has less. So that will partition off the clusters so that my user has more access to resources. Topology eviction strategies allow you to define when a topology should be evicted, meaning undeployed. So let's say you have a production topology, you deploy that, and to allocate all the resources that it needs to kick out some of your dev and test topologies is able to do that. And one of the more interesting features is rack awareness, which lets you to define how what your network topology looks like, and Storm will try to schedule things so that components are within the same rack, so the inter-process communication is a little faster. So what's coming up in 2.0 and beyond? So right now we're in the process of moving from Clojure to Java. Whenever I talk about this, or when people ask me why, I ask everyone, raise your hand if you feel proficient in Java. Now raise your hand if you feel proficient in Clojure. So what that's doing, we're expanding our community, so the number of people that can contribute to it. Clojure can be, to a standard Java programmer, Clojure can make their eyes bleed. I know the first time I saw it, I was like, what have they done to Java? Eventually I came to like it, still like it, but we want to expand our community, and the community made that choice. We also received a JStorm. What Alibaba did was do all this work before, and they called it JStorm. And they contributed that back to Apache Storm. The problem, and the reason why we can't just switch over right away, is all those 0.10 security features. So JStorm doesn't have any of those security features. So now we have to re-implement all those security features in Java, whereas before they were in Clojure. Performance improvements. Some in the community have been looking at ways to reduce the number of threads that Storm uses, and also replacing the disruptor queue with JC tools, which is a set of primitives for improved concurrency. And some of the benchmarks we looked at from moving from disruptor to JC tools look really promising in terms of throughput and latency. And I mentioned earlier, overhauling a threading model, so we're reducing the number of threads. How many people have heard of Apache Beam? Okay, so Apache Beam is a unified API for dealing with bounded and unbounded data sources. So similar to batch and streaming, where bounded is batching, streaming is unbounded. Storm has always traditionally been just unbounded. So with Beam, you have one API and multiple implementations. So right now there's Google Cloud Dataflow, Flink, Spark, and several others. Time's up. We have a break after this, though. So do you mind if I continue? If anyone needs to leave, I'm almost finished. So in order to support that, we need to implement bounded spouts. So what we're doing there is now we're including batching in Storm. So bridging the gap between bounded and unbounded models. In the next version, and this may actually come out before 2.0, is a new version of Storm metrics based on Codahale's metrics library, which is a lot simpler and easier to use than the built-in metric system in past versions of Storm. It's easier to specify user-defined metrics, and it will also include multiple reporters, so reporting to different systems like Ganglia, Graphite, Elasticsearch, what have you. And finally, this is coming out of JStorm, is worker class loader isolation. So the way we've been dealing with this now is we shade all Storm's dependencies and relocate them to different package names so they don't collide with user dependencies. And what this will do is do that for you, or do that for us. So user libraries will be isolated at the class loader level from internal Storm dependencies. We also have an upcoming improved back pressure implementation. The current one is a little naive, but the new one that we're looking at is a lot more robust, and will actually, rather than just throttle spouts, will throttle at the component level. And finally, dynamic topology updates. So this would allow you to update a running topology without undeploying it, without stopping it, and changing the configuration without restarting. And that's it. Thank you. Are there